Okay, so I'll just tell you a little bit about my background. Again, I'm Kai Cole. This is my 4th year here at Oklahoma State. I'm originally from Oklahoma, but I went to school, did all of my work at the University of Arkansas. So I've stayed pretty central, haven't traveled a whole lot like many of you in this class. But my PhD, my background, my undergraduate is in pure mathematics, and then my master's is in statistics. And so my PhD, I needed something a little more applied. I loved teaching. I liked testing, even though it kind of had a bad connotation at the time. So a degree in educational statistics, we call it REMS, Research, Evaluation, Measurement, and Statistics, but it's in the College of Education, applied to education, health, or anything like that. So my research is more on the psychometric side of it, so kind of putting the metrics to psychology, if you will. You might think of the testing industry with ACT and ETS, and they have these whole groups of people that nitpick every item that is written on the ACT, and it's multiple choice. And so what are the distractors, and why are they putting those distractors, and how are they scoring and reporting and things like that? But also more on the psychology side of it, I've done a scale where we administered, it was an anxiety scale actually, and we had positively and negatively worded items, and we wrote them so that we thought they were exactly opposite. So maybe I am happy, and then further down there was one that was I am not happy. And you would think, on a Likert scale, 1 to 5, you would just pick the opposite one, but that's not actually true. And so the way that people respond differently to positively and negatively items, and the way that we use statistics really to see that and to see trends across different cultures and how that's viewed as positive and negative and different things like that. So that's more of my research in depth. But in terms of ANOVA, it's much more applied, kind of on the surface, very common across a diverse setting. And so that I hope, my goal is that whatever interests you come in with, that you can figure out, oh, so if I did a project like this, then I could use ANOVA, that type of analysis, to analyze the data that I'm going to gather. And so we're actually going to start today with inferential statistics in terms of research methodology. What does it mean that we can gather a group of people together, evaluate them, collect some data, and then make conclusions that generalize to the population? So as we get started, we need a research scenario for the day. So I need y'all to help me out. So help me fill in the blanks here. It's like, what do they call these? A Mad Lib? Okay. So is there a significant difference in what between group 1 and group 2? What should we go with today?
Grades.
Grades. Okay. So maybe GPA for college grades. Okay. So is there a significant difference? Let's get set up here. In GPA between what group and what group? Males and females. A pretty common differentiation. Okay, so in this, we're going to kind of do a review. Like I said, I hope that you don't come into this class really intimidated and thinking, oh, it's the one class that I don't want to take, the one class I just need to survive. I hope that by the end of it, you actually enjoyed it, that you learned something. But we are going to start at the very beginning, because even though there were 2 prerequisites for this class, some of you guys had it maybe last semester, perfectly fine, you're just on a roll. Some of you had it at a different institution, perfectly fine. Some of you had it 2 or 3 years ago, so we need a little brushing up. You saw in Brightspace that there were some review videos. That's where I'm going to pick up, and today we're just going to make sure we're all on the same page. So today we're starting with the basics, okay? What is the independent variable in this research question? Gender. Is gender a nominal, ordinal, interval, or ratio scale of measure? Nominal. Why is it nominal? Because we're putting people into categories. One is not necessarily better or ranked higher than the other. Good. So that's a nominal variable. And what is our dependent variable? GPA. Now, what scale is that on? What's the difference in ratio and interval?
Absolute zero.
It's that absolute zero thing. So does anybody ever have a GPA of 0? Theoretically, yeah, but is it on like a continuous scale? Not really. So I would say that GPA is on the interval scale. And to be honest, there's a lot of different scales that could be debated. And you could argue your case that GPA is a ratio, and by the end of it, I might agree with you. The Likert scale, 1 to 5 is another ratio or interval, because we could, just alter it a little bit. And so we're not going to get into that debate in this class. But as long as we have just kind of that general understanding, I'm okay with it. So in inferential statistics, we use these to determine the probability or likelihood that the conclusion based on the analysis of data from a sample is true in the population. So our goals are to measure the effects of our independent variable and to make a valid generalization from the sample to the population. So you might think of our male-female group in terms of the population, every maybe college student, male and female, and then we just gather a small sample of maybe 10 male and 10 female, and we try to gather data from this small sample in order to make a generalization about every male and female college student. So a review of our notation, and this is important because we're going to get into some formulas, some equations, and if we don't know the notation, it's kind of like knowing the language, we're not going to be able to understand it. So let's just review some of those symbols from your prior courses. If we talk about population size or the number of people in the population, what might that be? N. And what about a sample size? How does a sample size differ in that notation? It's just a lowercase, exactly. What does the population mean? Mu, good. And what about I'm going to put MU. So this is the Greek letter M, I don't know why it's doing this. MU. Okay. Okay. And then what does the sample mean symbol?
X bar.
X bar. Good. I'm going to go ahead and come down here. Let's call group 1 male, and let's call group 2 female. So far, in the population of all males, we might have a mean mu male, and over here, a mean mu female. And then what is population variance? Sigma squared, another lowercase Greek letter. This is sigma. A lot of Greek in this one. What is sample variance? S squared, good. So just like our population of males has a mean mu, it also has a variance, and I'll call it sigma squared male, and a variance for the female group, sigma squared female. Now I could also talk about the sample here. So maybe you guys are my sample, okay? Let's just say that. You're the sample of all of the OSU college students that we're trying to make inferences about in the population. So let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 female. So over here in for my female group is 9. And for the male group, we have 1, 2, 3, 4, 4. And now you guys, I could ask you, what is your current GPA? I'm not going to do that. But what is your current GPA? And the male would have an average GPA, and the females would have an average GPA. And from that, we could also calculate the variance of the male GPA and the variance of the female GPA. What is population standard deviation? Just regular sigma and sample standard deviation. And what is population correlation? Rho, because the population stuff is typically a Greek letter. So we're going to use rho for population, and for the sample, it's R. What is correlation? Relationship. So if we wanted to say, well, how is the GPA of male and female related? It might be rho male female. Yeah. Good. Started good on that notation. Any questions? Okay, so when I talk about populations and sample, again, the population here is going to be all male and female students. And this is the population distribution. That's the distribution of GPA as it is in the population. So maybe, you know, the average GPA might be, for grad students, it's going to be higher, but we'll just say it's a 3.0. And maybe that GPA in the population looks like that. Then we could talk about a sample distribution. This is the distribution of a random variable, we'll say GPA, within a single sample of size n. So I want to take a sample of 10 people. What is their GPA? And another sample of 10. And what is their GPA? And another sample of 10. And that might have been, you know, the higher group. And there's their GPA. And so we're taking all of these different, theoretically, we're taking all of these different combinations of the same size. And for each of those, they would have an X bar. And what is an X bar? A sample mean. So this last step is the sampling, L-I-N-G, distribution, or the distribution of sample means. This is the distribution of sample means from all possible combinations. So once we have this first average, second average, third average, this last sampling distribution is really the distribution of the X bars from all of those prior samples. Why is that important? Why do we need to know that? You can use this link down here, that simulation link. It's really good. I have a video in your Brightspace that walks you through that. And it just goes through this in a little bit more detail, a little more visual, if you will, if you have trouble understanding this whole sampling and distributions. But why is that important? From that, we have the central limit theorem. And this is like the only theorem for the class. I know it's not a theory class, but it's the one thing because it's the foundation of research. It's the foundation of how do we gather from a small sample and generalize to the big population. The first rule of the central limit theorem is that the distribution of sample means, this one down here, is approximately normal regardless of the distribution of the population. Anybody think, why is that important? Why does it matter that the sampling distribution is normal? Say that again.
The average will always pull in the center?
The average kind of pulls into the center. You see it has that one single peak that everybody kind of falls into, funnels into. Why specifically normal distribution?
Symmetry.
Symmetry. There's a lot of symmetry. What do we know about the normal distribution? It's a bell curve. You remember z-score? Yeah. The normal distribution is like the gold mine in statistics. We know, if we know something follows a normal distribution, we can understand almost everything about that distribution. We know its mean, its median, its mode. We can calculate a standard deviation. I can tell you where you fall on that bell curve. I can say where you fall on the bell curve. So if we know that it's normal, we can draw a lot of different conclusions from that. The second one is that the mean of the distribution of sample means, this one down here, the distribution of all those X bars, the mean of that one, where its center lies, is equal to the mean of the population. So think about that. So this X bar of all X bars, okay, so it's the mean of this distribution of sample means, that is equal to whatever the X bar or whatever the mu is up there. And it doesn't matter if the population is normal. The population could be distributed like this, or like this, or it could be some crazy distribution. We don't know what it is, and that's okay. But if from the population, we took all those different samples and calculated their means, you're just one sample. We could take another one and another one and another one, and look at that sampling distribution, then the average of that would equal my population mean, which is what I'm trying to make inferences about, right? Oh, we have a connection. The last one is that the standard deviation of the distribution of sample means. I'm going to stop there. On this normal distribution down here, what is a standard deviation? What does that mean in terms of that curve that I drew?
Area under the curve.
The area under the curve, what did you say? Distance from me, how spread out that curve is. So the spread of that distribution of sample means, or the standard deviation, is equal to the spread of the population distribution divided by whatever my n was here. So this was sigma squared. Or I'm sorry, not squared, just sigma, just sigma, just sigma. So if I take the population sigma, that standard deviation, and divided it by the square root of all of these sample sizes, because they're all equal, then I would have the standard deviation of that sampling distribution. Another connection, and if we know mean and we know standard deviation and it's normal, we pretty much know everything. And that's going to give us the ability to make inferences about the population. Let me give you one more illustration of this. Let's say that this is the population. So I have 1, 2, 3, 4, n equals 5 data points. Okay, that is the population. It's a size of 5. I know it's small. But that is this distribution here in the population. if I took all possible combinations of little n equal 3. So here's one sample of 3. Here's another sample of 3. I'm taking all possible combinations of samples of size 3, and from those, calculating a mean. So these are means of the sample. Don't know why those are disappearing. Does anybody know why that's disappearing? I'm not familiar with the smart board. Okay, so you get the point though. I'm taking all possible combinations of that sample. So why? What do I know about these means, these little averages from all these little samples? I know these 3 things. I know that the distribution of these values, I just went ahead and worked it out for you. What does it look like? It's normal. Even though, look at the population. That's not anywhere close to normal. But we took all samples of the same size and took their averages, and we get a normal distribution. You know, like if you just have some extra time on your hands, go home, make up 5 new values, take all possible combinations of 3, and look at those averages in the distribution. It'll work every time. Next, let's do this calculation. So, did you bring a calculator today? Or maybe your phone. Your phone works for small stuff in class, but I would recommend that you bring a calculator to class. Specifically, this is as fancy as you need. Something that will do squares and square roots. If you have a graphing calculator, that's fine. But I would recommend that you get a calculator and bring it because you'll need one for the exam. And for the exam, I don't let you use your phone. So something like this, okay? First, calculate the population mean. What is mu of my 5 numbers up there? Eight. Good. Now, calculate the average of those sample means that we took. What'd y'all get? 8. That'll happen every time. The population mean will equal the mean of all of your sample means. The last one, and I won't make you calculate standard deviation. I'll assume that you know how. If you don't, there's a video back there that'll remind you how. But if we took the standard deviation of these values, it would give us 0.894. If I take 0.894 and divide it by the square root of n, because this was n equal 3, then I'm going to get 0.516, which should be the standard deviation of those sample means. Okay? So do you kind of have a concept of the central limit theorem thing a little bit? Okay? This is the foundation of how can we have a sample that we make inferences about in the population. So standard error of the mean, that one's pretty important. This is called the standard error of the mean. Is the measure of variation in the distribution of sample means. So this is that same formula, number 3 of the central limit theorem. In practice, we don't know the standard deviation in the population because we don't know anything about it. But it's common to use the sample standard deviation that we have in order to calculate and estimate this standard error. So this is a formula that you would use for the standard error. What do you think about this? The larger the sample size, the blank, the standard error. If you were to guess, what would you say?
Less.
Less? Okay. Let's see if that's true. Say that the sample standard deviation is 10, it's fixed. And that came from a sample of 25. What is 10 over the square root of 25? 2. Let's say, no, actually, that standard deviation came from a population of 100. What is 10 over the square root of 100? 1. So when we increase the sample size, we did what? Decrease the error. Why? Let's conceptualize that. Why, when we increase the sample, did our estimate of error go down? Yeah, because we're getting a better average. Clearly, if I have a class of 13 and I'm trying to estimate, I don't know, 25,000, might do an okay job. But if I had a class of 100, I would do somewhat better at estimating 25,000 people, right? So the larger the class, the better representation we're going to have in that class to estimate the population. Yeah. So what is the difference? I just want to clarify the difference in just a plain old standard deviation and a standard error of the mean. So standard deviation reflects how close the observation comes to the sample mean. So this was the formula for a sample standard deviation. You remember that? Okay, so let's say I have a sample of 9, and here is the average of those 9 observations. So a standard deviation is a measure of how close these 9 values come to its mean. But a standard error for a given sample reflects how close the means or averages of repeated samples come to the population mean. So let's say here's sample 1, here is sample 2, and here is sample 3. Each has 9, and each has its own sample mean. Well, if we would put all of those groups of 9 into one population, and that population has a mean, then standard error says how close are my sample means to that big population mean. So it's just kind of what comparison am I making? Now I'll say here, when you go out and do research, are you going to collect all possible combinations of samples of size 10 or 20? No, you're going to probably collect one sample. If you're lucky, you replicate it and do 2 different samples. But you're just going to collect one sample. But this is still the underlying foundation of what allows us to make those generalizations to the population. Do you have any questions so far? I know I just kind of jumped right in. Welcome. Do you have any questions at all? Okay, good. So now I'm going to review hypothesis testing. When I say hypothesis testing, what does that make you think about? What do you think? Reject or fail to reject. That's a good one. I like that. What else? Variables.
You know if an assumption is true or not.
Yeah, to figure out if an assumption is true or not. Good. So whenever we learn about hypothesis testing, textbooks, instructors, different classes, you might learn these steps in a different way. They might be flipped, they might use different terms. So that's why we're going to use these same terms throughout all this class, and NOVA is a form of hypothesis testing. So that's why today I just want to give you the bare basics of hypothesis testing to make sure that even if you learned this somewhere else or from another person, that you realize what terminology I'm going to use and connect it with what you already know. Okay, so I use 5 steps for hypothesis testing. The first one is always the research question. The second one is the hypothesis. The third is the level of significance and critical values. Between steps 3 and 4 is where I would actually collect data. So there's not a whole lot of, in the hypothesis testing, if you're really intimidated by math or formulas or anything like that, steps 1, 2, and 3, no formulas yet. You're good to go. The only step that will actually calculate something is step 4. When we calculate, and then 5 is the conclusion. So the first step is the research question. And the research question is not specific to the ANOVA class. We have research questions in ANOVA, in multivariate class. How many take regression? Anybody going to take regression after this? There will be research questions that are appropriate for regression. So the goal in step 1 is to define that research question well enough, identify the variables, so that we know, oh yeah, ANOVA fits with that type of a research question, not regression or a chi-square test or another type of test. But ANOVA fits that type of question. That's why it's always the first step before you gather and you analyze your data. The question should be compelling, interesting, researchable. It's hard to, whenever you're writing a dissertation, is anybody in that process quite yet? Okay, whenever you actually define your research question and you want to look at all of these different variables and all of these relationships, and then you need to fit it into one question, it's like one question becomes a paragraph, becomes a page really, really easily. But somebody once told me, your dissertation is not intended to solve the world. It's just intended to make one step. And that's good, because how many want to, after you finish your dissertation, how many want to continue doing research, maybe a faculty position or something like that? Okay, so some of you won't continue your research, and that's okay. But for those who are, you don't want to solve the world with your dissertation because there's more to solve after that. You know, so think of it like that. What's going to set me up really well for the future? What's going to make a significant contribution, but that's also going to leave room for me to grow and to continue what I've started while you're kind of under the umbrella of an advisor, learning how to do research. And then whenever you step out, you can keep going. You don't need your advisor anymore, and you keep doing it on your own. So in order to investigate, new research is necessary. So that chapter 2, that literature review of what's been done, that was always my fear, that I was going to get, you know, onto the last page of writing and then realize, oh my gosh, somebody already did this. So chapter 2 is important. You know, you have a strong background so that what you do is new. It has a good balance of breadth, specificity, but the question specifically needs to identify the variables. What are they? What is the relationship that you think may exist among those? So your question is going to tell you how to conduct the study, what type of data, what type of analysis, and the direction of the relationship. So it really is step 1. So I hope that you love this class, but I hope that at the end you don't think, okay, now I need a dissertation that I can do ANOVA with. I don't want you to think that. It's just one of many, 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 many. Because then you're going to take maybe regression, and you'll think, oh, well, that's great too. So what you're doing is you're just building a toolbox. You know, you have the hammer and the wrench and the whatever, screwdriver, so that whenever you have a research question one day, you say, okay, what tool do I need? Because I have a toolbox full of analyses. I'm not going to use them all, but I'm going to use a few of them. And so this is just one of those pieces. I give you some example scripts down there. So types of tests that I hope that you would have looked at up until this point is maybe a Z-test or a one sample t-test. How many of y'all have seen that before? Perfect. What about an independent samples t-test? Great, that's what we're reviewing today. A dependent samples t-test? Good. And then how many people have done a full ANOVA? Full ANOVA test? So maybe half of you, and that's okay. So not everybody in their prereq went all the way through to ANOVA. You've all done, it looked like an independent samples t-test though. What was an independent samples t-test?
Two independent variables.
Two independent groups, like, is there a difference in GPA between male and female, right? Okay, so ANOVA would take that one step further. Just add in another group. Is there a difference in GPA among freshman, sophomore, junior, senior? It's just taking your independent t-test that's only for two groups and adding a little bit more to the analysis so that you can have 3 or 4 or 5 groups. So you're really just expounding on what you know. That's why we're foundation today. We're reviewing that independent t-test really well, and then next week we'll do ANOVA. So our hypothesis, an educated, assumed statement of fact that guides our investigation. So a statement regarding the values of one or more population parameters. So I'll say the hypothesis is not about the sample. So just kind of let that soak in. It might seem intuitive. You gather data from a sample. I can clearly see that maybe males have a GPA of 3.0 and females have a GPA of, we'll say, 3.1. Okay? Is that different? Is 3.0 different from a 3.1? Yes, numerically in the sample, it's different. We see it. I don't need to test that. What I'm testing to see is, okay, is that 0.1 difference big enough so that we can conclude there's probably a 0.1 difference in the population? Or maybe, ooh, that's too close. They're probably, going to be the same in the population. 2 hypotheses. What are they? Null and alternative. So the null hypothesis is always a statement of no relationship, no impact, no difference. And this is the one kind of innocent until proven guilty. We are going to hold on to the null hypothesis as long as possible and assume it's true and then test against it. In the end, we'll either reject the null because we proved it wrong, or we don't prove technically. So we gather data to support an opposition of the null hypothesis, or retain or fail to reject the null. The alternative is what we're most often seeking, that there is a relationship between variables. And so, yeah, we want to show that there is a difference, there is a significance, but sometimes it's a Debbie Downer if we don't. Have you ever, kind of encountered that? Oh, no different. But that's okay. In some cases, it's just as valuable to know what's not different as to know what is different. So a non-directional hypothesis we will call a two-tailed hypothesis. This indicates that 2 group means are different. If my null hypothesis, and again, we're hypothesizing about the population, so my hypothesis involves those mu's. What do those mu's represent? Population means. So that's why we write our hypothesis in terms of those population parameters. The null is mu1 equals mu2, that the 2 groups have an equal mean. And what is the alternative, do you think, for a non-directional? Does not equal, yeah. So this keyword was different to indicate to us that not equal sign. Directional, we could either have a right-tailed test or a left-tailed test, indicating that the mean of group 1 is greater than, or that the mean of group 1 is less than the mean of group 2. So what sign do you think is going to go in this between the mu1 and mu2 in this alternative? Greater. And what about this one? Less than. But notice that the null hypothesis of all of those is what? It's always equal to, because the null hypothesis, regardless of what direction you're hypothesizing, the null is always that equality or no difference. When you write mu's or x bars or any type of notation, you can always put a subscript male, female, or whatever it is your variables are, just to indicate to you and to clarify to you what those groups are, but it's not necessary. So a non-directional hypothesis or a two-tailed indicates a significant difference. And that's kind of a key word in a statement, a difference. It doesn't indicate the direction of the relationship. So let's look back at this null hypothesis, mu1 equals mu2. If I subtract mu2 from both sides, would you agree that that statement is equal to mu1 minus mu2 equals 0? Okay, good. So that's what I'm going to work off of instead. That means over here, assuming that the null hypothesis is true on this normal distribution, it's going to be centered at, I'm assuming there's no difference, that mu1 minus mu2 equals 0. The alternative you said is mu1 does not equal mu2. And what would that be in terms of kind of that adjusted or transformed version? Good. Mu1 minus mu2 does not equal 0. So that means that if I'm looking at male and female GPA, if they don't subtract and equal 0, so 3.1 is different than 3.0, we know that. It doesn't exactly equal 0, but can we give ourselves just a little bit of room on each side to vary so that when we make inferences about the population, we take into account that sampling error that might have been present in that specific sample? So this is how a confidence interval is used to test a difference in two group means. If the confidence interval contains 0, the null hypothesis is agreed with. So we would say no difference. But if we subtracted those values, mu1 minus mu2, and it was less than whatever this criteria or greater than that criteria, we would say that there is a difference. So sometimes you just get confidence intervals for things. We want to know, well, is that significantly different? If that interval contains 0, then we would say it's not significantly different because we gave ourselves a little bit of wiggle room on both sides, and that fell within that region. Sometimes, though, we talk about a directional test, a one-tailed. So a left tail would indicate mu1 less than mu2, or mu1 minus mu2 equals 0. In that case, we're only allowing something to substantially differ on the left side, on the left tail.
Wouldn't it be less equals?
Oh, I'm sorry. Yes. Thank you. Always stop me if you find some mistake like that. I get a little carried away sometimes. Or a right-tailed test where mu1 is greater than mu2, or mu1 minus mu2 is greater than 0. Well, that doesn't mean that it has to be exactly greater than 0. It's not what we're saying. It means that we're going to give ourselves a little bit of wiggle room, and if it's greater than whatever boundary we determine based on how much error we're going to allow in that conclusion, then we have that value that will determine our cut point. Okay, so let's stop, take a breath, recoup, and on a piece of paper, I want you to write a research question that compares two groups, and it has one dependent variable, and then I want you to write what is your null hypothesis and what is your alternative hypothesis. So for me, it would have been, is there a difference in GPA between male and female? The null hypothesis is that there is not a difference in the GPAs, and the alternative is that there is a difference in GPA. Okay, so take just a few minutes and write your own research question.
Are we going to hand it in?
Yeah, you'll hand it in, so put your name on it too. And you can like tear it off or put it on a scratch paper or something. Okay. We won't have everybody share, but I'm just curious. Maybe two people Would you care to share your research question? Yeah.
Mine was, is there significance in behavior between low SES and high SES adolescents?
Nice. Is there a significant difference in behavior between low SES and high SES youth, adolescents? Adolescents. Nice. How would you measure behavior? Just out of curiosity. How would we measure behavior? Anybody? Do what? Office referrals. Yeah.
Number of tantrums in a day.
Number of tantrums in a day. Good. Good. So what is your null hypothesis for that question?
I don't know if I'm seeing this right or not.
That's okay.
I said there is a difference in behavior between low and high SES adolescents.
Okay. That one's going to be your alternative. Whenever you say there is a difference, that's your alternative. So what is the null hypothesis? There is no difference in behavior between low SES and high SES. Yeah. Okay, great. One more. Yeah.
Is there any difference of motivation to study between domestic and international students?
Nice. Is there any difference in motivation to study between international and domestic students? Interesting. And how would you measure motivation?
By a standard scales.
By a standard scale.
Yeah.
There's a lot of motivation scales out there. A lot of people will do survey research or, just use an instrument or something like that. So what is your null hypothesis?
There is no difference of motivation to study between domestic and international students.
There is no difference. And what is your alternative?
There is significant difference of motivation to study between domestic and international.
There is a difference. Very good. Very good. Any other questions about steps 1 or 2 in this process? Okay. The next one is step 3. This is a critical value and level of significance. These determine the critical value, the confidence and level of significance determine the critical values which separate that distributions into regions where the null hypothesis is rejected and where it is not rejected. If I go back here, my critical value is actually this number right here on the axis that separates no difference from there is a difference. No difference from there is a difference, or there is a greater difference. These come from a distribution table. So since we're doing a t-test, that means we need a t-table. So I have one here for you. So specifically, and there's a lot of different t-tables. If you just Google t-table, it'll bring up a lot of different ones. This is the one that I like. For this, we need to know 3 things. We need to know the direction of our test. Is it one-tailed, two-tailed, right-tailed, left-tailed? We need to know the level of significance. For this, you might also say the confidence level. And then we need to know the degrees of freedom in most cases. And for our 2 sampled test, it's going to be the sample size total in both of the groups minus 2 because we have 2 groups. So we'll get to this in just a bit, but I wanted you to note, so these numbers are actually going to be those dividing lines on that normal distribution curve. The rejection region, so you can tell we're getting close to the conclusion because that's one of those words that we would use. The region is the range of values from the observed data for which the null hypothesis is not probable, and it's in the direction of the alternative hypothesis. So if I have a right-tailed test, like this one is a right-tailed test, so whatever value, critical value I have, my rejection region is going to be over here. If it's a left-tailed test, that implies my critical values over here. And on the left side, I have a rejection region. And this is where the null hypothesis is not true. So this is H naught is true. And this is H naught false. H naught true. H naught false. The area of that rejection region is equal to alpha, and alpha is a level of significance, a predetermined level of probability of rejecting the null when it's actually true. Wait a minute. We don't want to reject when it's true. If the null hypothesis is true, we want to fail to reject it, right? But in statistics, there's always this chance of error. We're never 100% certain. Remember, I pulled my word back when I said I proved it. That implies 100% all the time, no error. Well, that's not always true. So we give ourselves this level of significance. What level of confidence? Do I want to be confident? I can't be confident 100% of the time. It's just not possible. Do you want to be 99% confident? So 99% of the time, you're going to make the right conclusion. Or maybe 95% of the time. 95% of the time, you're going to reject the null. I'm going to say, there's a difference in male and female GPA. Oh, and really there wasn't. We don't want to do that, but there's always that chance. So you have, it's predetermined. This is where you have some control on how much error am I going to allow into my research study, into my conclusion. So common values are 0.1, 0.05, and 0.01. And it's, again, related to that level of confidence or the probability of making a correct conclusion. So let's say 95% of the time, I want to make the right conclusion. So 95% over 100% is 0.95. And that leaves what as alpha? 0.05. So when we choose an alpha level of 0.05, I'm saying I am 95% confident that I made the right conclusion. What about if alpha is 0.01? What is the level of confidence? 99%. Good. Very good. So again, here in my rejection region, the area equals whatever alpha is that you chose. So alpha, oh my goodness. Let me change colors here. So the area of this rejection region tail equals alpha. And over here, the area equals alpha. Again, you get to set it. So if you, let's think about this. Let's say just for example, I have two curves, okay? Centered at 0, centered at 0. If this one is 95% confidence and my tail looks like this, but this one over here is 90% confident. Is the tail going to be bigger region or is it going to be smaller region? Bigger region. So this one might have a larger tail if it's 90%. And notice how that might change your conclusion. So in the first one, you need a difference of that much in order to make it into that rejection region where you say, yes, there's a difference. But if you only want to be 90% sure, you don't need quite as much of a difference. So you have control, but this is step 3. This is not step 5.5. Like, oh, I made a conclusion. Ooh, can I change my alpha so that that line is in a different place? I can make a different conclusion. That's not good. We set this here, and then we start doing some calculations. If you have a two-tailed test, then we want regions to the left or to the right. And if I say that the total rejection region area equals alpha, how much of it is over here? Yeah, area is alpha over 2. And area is alpha over 2. Good. So what are they? How do I determine what those actual numbers are? We'll use this table of critical values. So first off, you'll notice that they are all positive. If this is my curve centered at 0, what you see are all of the positive values. But because that looks like a normal distribution, what do we know about it? It's symmetric. So the positive values over here that align with a certain alpha is going to be the negative value over here that aligns with the corresponding alpha. So we need to know the 3 things. What were the 3 things? Look back. The alpha, degrees of freedom, and direction of the test. So the direction, if the direction is 1-tailed or 2-tailed, that will determine if we're looking in that first row or in that second row. Level of significance. So these are the actual alpha values. Notice 0.05, the first one, the most common one, alpha 0.05. But there's also a 0.05 in the 2-tail. So we need to know if I'm doing a 1 or a 2-tail. The third thing is the degree of freedom. And so that's here, all of these numbers, N1 plus N2 minus 2. On your next slide, I have 4 questions. We'll do the first one together, and then I'll let you do the next 3. What is the critical value? So I have a right-tailed test, alpha 0.05, and degree of freedom 10. That tells me I'm going to have a right-tailed test. Is right 1 or 2-tailed? 1-tailed, okay. Right-tailed, alpha 0.05 here. And degrees of freedom 10. So I put all of those things together. And what is my critical value? 1.812. So here on the next slide, I would come over centered at 0. Here is positive 1.812 because it's a right tail. It needs to be on the right side. Okay, so y'all take a minute and do the next 3 with your neighbor. You can work with a partner. I'm sorry? No, you can write it in your notes. You won't turn this in.
Just trying to read it up, sorry.
Oh, yeah, no, you're fine. Let's see, I'll break at slide 40, so you can go ahead and go.
Oh, yeah. I was like, I didn't see that too crazy. Last time, oh, this is 5 years.
Yes, so it's gonna come from the tails, that's a good question. Sure, the tails. Because if it was in here, this is where it's most normal. So if you think about it, it's always on there. That's why you work that against the deviation.
With my impact to scale. This is degree of freedom.
Yeah, so I don't know, I guess it just depends on what the scale is of the sample that we're working at. You know what I'm trying to say there? So like, we're just looking at it abstractly here. So when you split it up, you work your way in, and since it's two tailed, I don't think you would take vertical line. You're just seeing how much area is at the transaction.
Okay, it's kind of quieting down. So, what is a critical value? We have a two-tailed test, alpha 0.01, and degrees of freedom 15.
947.
Okay, 2.947. It's two-tailed. What does that mean? If I need a value on both sides, I need two numbers. Ah, okay. Minus 2.947 and positive 2.947. Two tails indicates 2 degrees of freedom. What about critical value for a left-tailed alpha 0.05 and degrees of freedom 5? Negative 2.015. I heard 0.15 most often. Yeah. And what about the critical value for a two-tailed test, alpha 0.05 and 10? minus 2.228, and positive 2.228. Very good. Good. Questions on those critical values? Okay, we'll move on to step 4. Again, now we're going to go calculate our data, go gather, do the fun stuff. We come back and we calculate a test statistic. So this is a statistic, meaning it's from a sample, used to determine the relative position of the mean in the hypothesized distribution of sample means. So it's calculated using sample data. We compare the test statistic to the critical value to determine if the observed relationship of the means is large enough or extreme enough that it's not merely due to chance. Here is our formula for the independent samples t-test. So this is why we reviewed that notation. Let's do it one more time. What is X bar? Sample mean. What is mu? Population mean. And let's mean. Recall, what was our null hypothesis about the relationship between our means and the population? Mu1 equals mu2 or mu1 minus mu2 equals 0. Good. Okay. What is N1 and N2? Sample size. And S squared. Sample. Oh. Okay, close enough. So our independent samples t-test formula, we're going to take our observed sample means and subtract them. And innocent until proven guilty. We're assuming that this is true. So what is this value here? mu1 minus mu2. That's 0. And then we take the square root, and some people like to type it all in their calculator at one time. Some people like to do bits and pieces. So I would recommend, let's see, I usually do this in 4 pieces, I think. So the numerator, and then that portion, and then that portion, and then there. And then you can kind of work up from that. But those are the 4 main pieces. So when we talk about it, I'm like, what did you get? If one of them's wrong, then we'll check those 4 and figure out where it's at. Okay? We'll practice that in the calculator also. But that's all of step 4. There's one calculation. Okay? Then in step 5, we make a conclusion. So again, if I'm just marking this up to start with, then for what I see here is a left-tailed test. So the same thing could be mirrored on the right side or for a two-tailed test, but I just want to kind of block out some things. I'm centered at 0, assuming that the null hypothesis is true. So in this area, H0 is true. If my critical value is on the left side, what is this region out here called? Rejection region, where H0 is false. And what is the area of this region? Alpha. Yes. If the observed test statistic, so now whatever you just calculated from that big formula, if it falls in the rejection region, so if it's out here beyond the critical value, the conclusion is to reject the null hypothesis. Again, because it's in a rejection region. That's why we call it rejection region. And just from what you have gathered from your own research, when we reject the null, what is p-value? Is it big or is it small? P is less than typically 0.05. Oh, did we talk about a number that was often 0.05? Level of significance, that's what it is. So in this case, p-value is less than whatever alpha you determined. The test is or is not significant, statistically significant. It is statistically significant, yeah. But we could also have this other scenario where the test statistic, well, it might fall here. It might not quite reach the critical value. And in that case, the conclusion is to retain. Or some would say fail to reject the null hypothesis. So it's in that H naught is true region. I'm accepting the null hypothesis. In that case, my p-value is greater or less than?
Greater.
It's greater, and the test is not statistically significant. Now, I want to talk just a little bit more about the p-value. The p-value is the probability of obtaining a result at least as extreme as the one that was observed, given the null hypothesis is true. So this is also the probability that what you saw, those differences, are due to chance. Now, do you want to do all this research and then say, oh, it happened by chance? No, that's why we want p-values that are small. The chance that this is wrong is less than 0.05. Less than 5% of the time, I'm going to make an error. When the conclusion is to reject the null hypothesis, p is less than alpha. And when the conclusion is to fail to reject, it's greater than alpha. So this p-value on our curve, it actually has a place on that distribution. It's the region in the distribution outside of the test statistic from step 4. So I'm going to give you one more good illustration here. Again, let me write these up. So this is H naught is true, H naught true. This is H naught false. Rejection region, area alpha. And this is H naught false, rejection region, area alpha. And I'm going to color it. I'm going to say this blue region here is alpha. And remember, you picked alpha. Sometimes it's 0.05, sometimes it's 0.01, but you got to pick it. Now, if I reject the null hypothesis, then my test statistic is going to be on this blue region or the not blue region. Blue region. So maybe my test statistic that I calculated is right there. This area outside of the test statistic, that area region is the p-value. So notice this red part is what compared to the blue part? Smaller. That's why p is less than alpha when you reject the null hypothesis. And over here, if we failed to reject, then where would my test statistic fall? In the white part. So maybe it's right here, test statistic. Still, everything past the test statistic, this red region area is the p-value. And what is the red compared to the blue on this side? It's bigger. P-value is bigger than alpha. So sometimes we just use that. We get an SPSS printout or we do some data analysis and we just go straight to that p-value. Is p big or is it little? But that's why it related to the test statistic that was calculated and then compared to the alpha and critical values that were prior predetermined and chosen by you. Any questions about this slide? This one's one that we'll reference quite a bit just because it kind of puts everything together. Here on slide 38, I just have all 5 steps of the independent samples test. So I think at this point we'll take a break, maybe 7-8 minutes, and then we'll come back and we will actually do an example calculation of an independent samples test, okay? Okay, so I think what I would like to do for this example is to give you time to work on it. I think y'all caught on really well, and I have full confidence in you. So in small groups of 2 or 3, I want you to go through the 5 steps for this example. We have 10 students randomly assigned to one of 2 groups with coffee while they studied a textual passage for 40 minutes. So here we have one group thought they had coffee, but it was actually only 0 milligrams of coffee. The other group actually got some coffee. It had 90 milligrams of caffeine. And then we measured the amount of learning that had taken place after they read this. So it was like a reading comprehension thing. And we have their scores and the sample mean and standard deviations. So from that, I want you to, here's our question. I want you to determine and write out the hypotheses, the critical value, calculate the test statistic, and then provide a statistical conclusion. So again, let's say we'll try to do it in 10 minutes. Work with a partner and see if you get through these 5 steps. Okay.
We can write both down.
So that's how I would do it.
We're not putting this in, right?
So,
No, you won't finish it.
So we can estimate.
Yeah.
Everybody
We're good.
sample.
We're good.
That's what we took the sample population.
Yeah.
Would be, so I guess we see your 2 groups, that just be like, we just need to create like our times of
one.
and see if we have any other more characters.
And then
You want to do that? You know what I mean? It's just a, so they're equal to know all of that.
Yes.
Oh, so it's a single difference?
That there is like.
Yeah.
Sorry.
All the notes.
So that is. Minus 2. And so that would be X bar plus X bar. So 8 plus 12. So this n represents the same. So 8 plus 12.
Alpha point two.
Yes, so like.
Yes, let's choose an alpha of 0.05.
So we just substitute. Those are increasing rates. Okay, real quick, we need to know what our.
Oh, okay.
Yeah. Now we why am I? No, that's our test statistic.
Oh.
Okay. Yeah.
Okay.
Oh, yeah, that's right. I don't think we're doing two tabs.
Yes,
If
exactly that.
there's a difference, so I think it's a two tab. Does that make sense? The question is about that.
Medium one minus one two.
That's what I was trying to figure out.
Okay.
We get to pick our own seat.
We have to do this all in our head.
It's 2.05.
Right, not for the top.
Oh, sorry, there you go.
So, 1/5.
Yeah. That is.
Say, I guess, for 1
0
kilograms.
Actually,
So.
that's right. So the critical value is the is that right? That's what I thought.
All of
Okay,
them.
so that's fair. I'm just gonna move over to you.
Here's the one that I like.
Or maybe not, she wants to stick up. You want to
S1 squared.
So we should absolutely that. Oh, minus 0 is 4.
Wait, 8 minus 12.
You wanted me to, or since it's the null, you just make sure you choose 0. You remember that? Yeah, we checked real quick, but like you assume these.
We'll figure it out.
Minus and
Plus minus,
Right. Exactly.
These ones are here.
That would be your sample.
Well, and I had it there.
we check the small.
Oh,
I might have it bigger on this next one.
0. That's what she had in mu is 0. The population situation.
I'm not sure.
That's what you hear.
Yeah, and 1 minus 2.
Oh, okay. Yeah. Yeah.
Yeah.
But
You ended up,
Oh, yes.
okay, there's S1,
N1
S2, so there you
is
go. Six, there's the S1, the 0.
Oh, okay.
You square that S1.
Oh, you're right, you're right.
No.
You want to double check?
Oh, yeah, okay. Variance.
1, 2 squared.
5 and minus. So that's down here is 1.
Yeah. Yeah, so you have 8 for the first one, then 12 will be the second one, so 12 minus
5 minus 4 over 20. Oh, that's all right. Yeah.
1, 2 squared.
So 8, over 5. I like to split it. So that's the other. Yeah.
Yep, take it 1 step
What or
Multiplying it smaller is all.
Give you 2 more minutes.
was 1
Yeah, so we just, yeah, so that's just decrease.
These are intermediate for 1.4. The course consistency course. Hey, you too?
Okay, for this example, we'll just pick it up. If you're not through, that's okay. We'll talk about all of it. What is the null hypothesis? There's no significant effect of the caffeine. How might we use some notation to write that out? Mu of the 0 group.
Equals
Yeah.
mu.
Good. Mu of the 0 group equals mu of the 90 group. And what about the alternative?
Mu of 0.
Good, because it just said there is an effect. It didn't say less than or greater than or give any type of indication. What were the degrees of freedom for this one? 8. 5 plus 5 minus 2 equals 8. At 0.05 degree level of significance, what is the test statistic? Plus and minus 2.306. So already I could come over here and mark negative 2.306 and positive 2.306. Yes. My question really just said, does it have an effect? So it didn't say, does it increase comprehension or does it decrease comprehension, or it gave no indication of some directionality.
Okay, got it.
Yeah. On my curve there, I've written my critical values. What is the rejection region area?
Below -2.
So everything out here is a rejection region. and everything up here is a rejection region. And we know that the null hypothesis would be true on the inside. The test statistic, let me write it out long form first. So my group means were 8 and 12 minus 0 divided by the square root of 5 minus 1. The first standard deviation is 1, and it needs to be squared, plus 5 minus 1, 2.12 squared, divided by 5 plus 5 over 2, multiplied by 1 over 5, plus 1 over 5. Okay, so that's the setup. Any questions about the setup? No? Okay, make sure you get all that. Okay, what did you get? Good. Minus 3.814. How many people got that?
1.6.
1.6? 3.14, okay. If I think about those three components that I talked about, what did you get on the top part? What's 8 minus 12? Minus 4 over the square root of, okay, what is just this piece right here? Mm-hmm. Say it again.
21.98.
Okay, 21.98. And then what is this piece down here? 8, because that's the degrees of freedom. And then what is this part right here? 0.4. Good. Okay, so now what we might do is just, what is everything here under this square root sign? 1.099, yeah. And then what is the square root of 1.099? 1. This is -4 still on the top. Don't let me forget that. -4 divided by 1.048. And then, I don't want that decimal there. 4 divided by 1.048.
Minus 3.816.
Good. So did we find our mistake if we didn't quite get there? Okay, good. Now we'll take that -3.816, come down here. I'll do it in green, and it's going to be somewhere out there, -3.816. So my conclusion is to what? The null hypothesis. Reject. We would say caffeine does have an effect on reading comprehension scores. Now, the way that we would write that test statistic formally is that we use a T test statistic. What were the degrees of freedom? 8. So T parenthesis 8 equals, and the value -3.816, comma, and now the p-value is what to 0.05? Less than. Good. So that's kind of our formal presentation of the test statistic. Yeah. Any questions about that? Good, you did good. Very good. So now I just want to talk through a few other things about the independent samples t-test. Again, because we're going to build on that when we go to ANOVA. First are the assumptions. We have 3 assumptions. The first one is that the data and the groups are independent. So this says that observed scores from one subject are not affected by scores from another subject. The GPA of one female isn't affecting the GPA of another female, nor is the GPA of all females affecting those of all males. The second one is that populations are normally distributed. So why might that be important or not be important? Notice that I have two curves here at the bottom, okay? And let's just assume that the distance, what we're trying to do in an independent t-test is determine, is this mean significantly different from that mean? That's essentially what the independent test is doing. And so I want to know, what is that difference? The same thing here. So let's just theoretically say that the distances between those two are exactly the same, okay? Now on the left-hand side, both of these distributions are what? Normal. Do they have very much overlap? Not a whole lot of overlap. So if there are differences, we're going to detect them, right? There's not much overlap. Over here, notice that this one is normal, but this one is really skewed. But the difference was the same. The difference in these means is exactly the same on both of these illustrations. But on the right-hand side, because I have this non-normal distribution, is there some overlap happening? Notice all this noise happening. Are we likely to detect these differences over here? No. We might, but we might not. There's a good chance that even though there is a difference, we won't detect it on the right side because the distributions are not both normally distributed. If we violate this, it doesn't generally affect type 1 errors except for skewed distributions where I have here. You see that skewness. And for this, we will use a Shapiro-Wilks test. So SPSS, we just click a few things. It gives us the actual test result, and we can determine if it's normal or not. The third one is that populations have equal variances. And the same thing kind of holds here. In addition to normality, notice that the distributions here in these two illustrations, the difference in those group means are exactly the same. On the left-hand side, I'll probably detect them because there's not much difference or overlap because the distributions are both so similar. But over here, because even though it's a bell shape, notice that it's a lot more spread out than the other curve. Even though they're both a bell shape, they don't have equal spreads. So even though they have differences in means, I don't see it again because those different variances cause a lot of overlap in those distributions. So it's there, I just don't detect it. Now, there's a caveat here. If sample sizes are equal, violations to this assumption don't severely affect the results of the test. One of the many reasons we like equal sample sizes. And again, there is a significance test like the Shapiro-Wilks. We could use Levine's test. So Levine's test has a null hypothesis that sigma squared 1 equals sigma squared 2, or that the groups have equal variances. This means the assumption is met. I'm assuming that we have equal variances. The alternative is that sigma squared 1 does not equal sigma squared 2, and that the assumption is not met. So in this case, when we test this assumption, do we want to retain or do we want to reject the null hypothesis? We want to retain. So most often when testing assumptions, a large p-value is desired. We actually want to retain the null hypothesis. So it starts to kind of confuse our minds because we're so used to wanting a small p-value, wanting a small p-value. But when you look at the assumption, think opposite. I don't want a small p-value. I want a large one because I want to retain the null. Okay? Time is it? Okay. So the last thing about effect size, error, and power. Effect size is the extent to which the intervention has an effect of separating two populations in standard deviation units. So, for instance, if we have an effect size of 1, that indicates that the group means differ by exactly 1 standard deviation unit. The formula for the effect size for the independent test is this right here. And notice it's so similar to the test statistic. What part is not included in that? 1 over n plus 1 over n. All we have to do is get rid of that part in our test statistic, and we've calculated the effect size. So I'm going to write this in. You know what those are. A statistical test reports the statistical significance. So think about this. Maybe back to our caffeine group. Okay, so did we reject or retain the null hypothesis? We rejected. When you tell your readers or you make this conclusion, I reject the null, caffeine has an effect. That didn't indicate to me if on our, remember on our curve that looked like this, we had critical values of positive 2 point something and negative 2 point something. Rejecting the null and making that conclusion doesn't really tell me if it was barely significant or if it was like really significant. I don't know. I rejected the null, which is like a win-win, but how much? And we can't say like we were partially significant or we were kind of significant or we were a lot significant. We don't use those words. You're just significant. So we need some other measure to kind of quantify how different they are, whether it's significant or not. And that's what effect size does. So the effect size is a measure of the practical significance. If we go back to our test and you look back at your data that you had already calculated, in the numerator of the test statistic was 8 minus 12 divided by the standard deviation of 5 minus 1, 1 squared, plus 5 minus 1 times 2.12 squared over the degrees of freedom. I'm just leaving off that 1 over n plus 1 over n, okay? So calculate that. What is that number? It had all the pieces.
Negative 1.4545.
Say that again.
Negative 1.45.
Did anybody else get that? It's not going to be negative, sorry. It's an absolute value. Typically, you can leave it. Nobody would, say, it can't be negative because that gives the direction, but typically it's an absolute value. Anybody else get an answer?
Oh, I guess.
Square root. Yes. So many pieces. So what's your corrected value? 0.56. 0.56. let's see, if I remember right, this was 4 over the square root of 21.98 over 8. There we go. 2.41 is my effect size. So this says that not only are these groups different because it's significant, we knew that the test statistic fell out there, but by how much are they different? They differ by approximately 2.4 standard deviation units. And on our criteria down here, is that small, medium, or large? It's 0.2, 0.5, 0.8. So the value of 2 is very large. Yeah. So not only is it statistically significantly different, but it's also practically very large. The effect of caffeine is very large in this case. You see how the statements kind of give some different information there? Okay. The last thing that we want to put blinders on, but you as a researcher are going to be educated and know that there is a chance of error. And I briefly touched on this, and I want to end today just talking about this so that we are aware. We have potential errors in a study. So let's go back to the, let's just talk about the caffeine one. Let's say that in reality, the null hypothesis is true, or no effect of caffeine. And in reality, there is an effect. So in reality, one of those two things are true. We're just trying to determine which one. And then we do this research test. Well, we determined that we rejected the null, that there was a difference. So which one in reality does that support? H naught is true or H naught is false? H naught is false. So this would be a true, correct conclusion. Remember when we were talking about level of significance, we determined alpha, 0.05. Alpha was the probability of rejecting the null when it was actually true. This is what we call a type 1 error. And the probability of that equals alpha. Let's say we didn't reject. Let's say that we did all that and we made this conclusion, there's no caffeine effect. Which one of these spaces, the left or the right, would be the true block? The left. This would be true or correct. And this would be another error that we call a type 2 error. The probability of that is beta. How many of y'all have heard the word or the term power as it relates to statistics? Yeah, so which of these up here, which of those 4 blocks do you think corresponds to power as you have understood it? Say it again. Bottom right. Bottom left. Top right.
Just throw it in there, top left.
Top left, why not? You have a 25% chance of getting that answer correct. Power is actually the probability that you reject the null and you determine there are differences when really there are differences. This is power. You might have thought bottom right because it's related to type 2 error. It equals 1 minus beta. So it's the inverse of type 2 error. Let me write those out in words for you a little bit more. So type 1 error is the probability of making a conclusion that there are significant differences in the population when really there are not. And this is rejecting the null when it's true. And the probability of that is alpha, determined by you. Type 2 is the probability of making a conclusion that there are not significant differences when really there are. This would be retaining the null when it's false. And this probability is beta. A little bit more about this type 2 and power. A closely related measure to type 2 is called power. And this is the probability of rejecting a false null hypothesis. And I'll put a smiley face because we like power. This is a good thing. Concluding that group means are different when really they are different. I know these statements sound so funny, but some of them contradict, and if they contradict, it's an error. If it doesn't contradict, then that's good. One of which those would be power. Just as 0.05 is a conventional level for alpha, 0.8 is a conventional level of power in your study. Now, the thing about it is, you don't get to determine power per se. You get to determine alpha, and that's about it. You go collect data, you make a conclusion, etc. But power is determined by your effect size, your sample size, a lot of other things. But your starting point is alpha. Now, there are things you can do to affect your power. Here's just a nice diagram of how these things are related. If you click, I like this. If you click on this link down here, it's another one of those simulations, and it'll allow you to kind of shift and change and see how these three are related. As one goes up, one goes down. As one goes up, one goes down. And you'll see how they are related. We will calculate power using this little software, G-Star Power. It's free. You can download it. I don't know if it's on these since they've been rebooted, but I'll check. But I'll talk you through that whenever we get there, but I want you to know how to calculate it, and it's a good resource for you to take from here. I went in and from this just calculated power for our example. So I'll point out a few pieces. I chose a t-test with an independent test, and then I want to compute the power. And it was a two-tailed test. We calculated an effect size of, remember, 2.4, yeah? And then an alpha of 0.05 and our two sample size groups. We hit calculate and it calculated power. So that's nice. I used to make you guys calculate this by hand and it was ugly. So thank you, G-Star Power, that we can put in some numbers, click a button and it gives us a number. Can y'all read that? It says power is 0.914. Is that good or bad? That's good. It's the probability that we concluded there are difference, which we did, when really there was. So there's a 91% chance you made the right conclusion. That's good. I said you can affect your power a bit by changing your alpha, your type 1 error rate, increasing your sample size. That would make sense. More people, more power, fewer errors, more homogeneous groups, more similar groups in terms of not that their means are similar, but that characteristics of the females are all similar and characteristics of the male are all similar. So maybe, you know, they are all from the business college in comparisons, that or they're all freshmen, or they all have an equal dispersion of other things that might affect their GPA. The more that we intensify or prolong the treatment, the more likely we are to see those effects if it goes on for a longer amount of time. A 1 versus a 2-tailed test is better, or a stronger research design. The second half of this class, we will talk about other research designs. The first whole half of the class is on the simple, basic, one-way ANOVA. So I don't have a whole lot of time left to talk you through this schedule and the syllabus. So I think instead of taking class time for that, I'm going to make a video. Maybe I'll make it tomorrow, and I'll just put that little video in Brightspace, and it'll walk you through Brightspace and the syllabus and the schedule and all those things. And then if you have questions, you can just email me about those. Is that okay? Okay. Y'all did awesome today, okay? I just want you to know, you just set yourself up really, really well. And I hope that I'm going to close this out. I'm going to upload this whole annotated PowerPoint into Brightspace with the link to everything. So go back and listen to the parts that you didn't know, review your notes, fill in the blanks if there are any questions. And then I have office hours on Tuesdays and Wednesdays. So shoot me an email or stop by, and we'll make sure those are clarified before we keep going. Okay? Your sheets that you put your questions on, please just pile those up here. Make sure your name's on it. And then I'll see you next week. You can put them over there. Yeah, thanks.